Hi class. So far, I've introduced two types of one-sample tests as an introduction to statistical significance testing: the one-sample t-test and the one-sample test of proportion. A one-sample test compares a sample statistic of a single variable to a known or hypothesized population parameter. In this video, we are moving to our first two-sample test, the independent samples t-test. A two-sample test compares statistics from two random samples. These samples must be independently selected from their populations. The purpose of the test is to see whether the difference between the two population parameters is statistically significant. Specifically, the independent samples t-test compares the means of two populations from which the samples are drawn. Let's look at an example. A researcher wanted to study the effect of study strategies on test performance. One mixed-gender group of 20 students was told to study for 5 hours the night before the exam. Another group of 20 students studied for 1 hour each night across 5 nights. Both groups then took the same exam, scored from 0 to 100, with higher scores indicating better performance. Assume both groups were randomly selected. The concentrated group had an average score of 75, while the spread-out group had an average score of 80. Both groups had a standard deviation of 5. The question is, do these two study strategies lead to different performance on the test? First, we need to be clear about the variables. There are two. The first is study strategy, a qualitative variable with two values: spread out versus concentrated. The second is exam score, a quantitative variable measured on a ratio scale. Since test scores are the outcomes of the study strategy, strategy is our independent variable, and exam score is the dependent variable. The independent variable splits the sample into two groups, and our goal is to compare the average scores, mu1 and mu2, of the two populations. Now let's summarize the data. Both groups have a sample size of 20. Group 1, the concentrated group, has a mean of 75 and a standard deviation of 5. Group 2, the spread out group, has a mean of 80 and a standard deviation of 5. We'll follow the same 5 steps as before. Step 1, state the hypotheses. The null hypothesis states that there is no significant difference in the average scores of the two populations, expressed as mu1 equals mu2 or mu1 minus mu2 equals 0. The alternative hypothesis states that there is a significant difference, so that mu1 not equals mu2 or mu1 minus mu2 is not 0. In step 2, we set alpha at 0.05. The degrees of freedom are calculated as n1 plus n2 minus 2, which is 20 plus 20 minus 2 equals 38. Using the t-distribution table, we can find the critical values for a two-tailed test plus minus 2.024. Next, in step 3, we calculate the test statistic, which places our sample statistic into a sampling distribution and helps us figure out how likely the observed value is to occur if the null hypothesis were true. The independent samples t-test uses the sampling distribution of mean differences. This distribution is theoretical. Imagine repeating the study many times with samples of the same sizes, recording the difference in group means each time, and plotting all those values. That distribution of differences forms the sampling distribution. The sampling distribution of mean differences is a normal distribution, the mean of which is the difference between the means of the population 1 and the population 2. The tricky part is estimating its standard error. Recall that in the one-sample t-test, the sampling distribution of the mean has a standard error calculated as the population standard deviation divided by the square root of the sample size. Things get more complicated here because we have two populations. The easiest way to estimate the standard error of the sampling distribution is to assume that the two populations have equal variances, and the two samples can be combined to estimate the pooled population variance, since a larger sample size provides a more accurate estimate. To do this, we compute the pooled variance by combining the sum of squares from both groups and dividing it by the total degrees of freedom. From there, we calculate the standard error by multiplying the pooled variance by the sum of the inverse of n1 and the inverse of n2, and then taking the square root. On this slide, there are two formulas. One uses the total sum of squares of the two samples to estimate the pooled variance. The other calculates the standard error from the pooled variance. They look complicated, but do not be scared because the computer can do the calculation for you. In our example, the pooled variance is 25, which gives a standard error of 1.58. The observed mean difference is 75 minus 80 equals -5. The hypothesized difference between the two population means is 0. Dividing -5 by the standard error gives us a t-value of -3.165. Looking this up in the t-table, the probability of getting such a value, if the null hypothesis were true, is p equals 0.003. In step 4, with all the information, we reject the null hypothesis since p is lower than alpha equals 0.05. And the observed t-value is beyond the critical values. Either way, we know that if the same study were repeated as many times as possible, the chance of observing a 5-point difference between the two samples is lower than the significance level of 0.05. In the final step, we conclude that given alpha equals 0.05, there is a significant difference, with p equals 0.003 in the average scores between students who studied in a concentrated way and those who spread out their study time. Now, you might ask, how do we know the two populations have the same variance? What if they don't? That is a great question. If variances are not equal, we would still run a t-test following the same steps, but we cannot pool the samples. Instead, we calculate the standard error separately for each group by dividing each variance by its sample size, then taking the square root of the sum. The degrees of freedom are also adjusted using a correction formula. For example, suppose we repeat the study with new samples. This time, the concentrated group has N1 equals 21, a mean of 70, and a standard deviation of 10. The spread out group has a sample size of 16, mean of 80, and standard deviation of 5. With the unequal variances, the standard error would be 2.51, which is the square root of the square of 10 over 21 plus the square of 5 over 16. And the adjusted degrees freedom would be 31. The observed t-value is negative 3.98 with p equals 0.0004. The critical value for degree freedom 31 at alpha equals 0.05 is plus minus 2.04. Again, the decision is to reject the null hypothesis. It's important to note that two random samples will most likely have slightly different variances just due to sampling error. To formally test whether the variances are significantly different, we use a separate test for equality of variance, which I will cover in another video. That result tells us which version of the independent samples t-test to use. A quick recap. Two variables are involved in the independent samples t-test. There is one dependent variable, which is quantitative, measured at either interval or ratio level. There is one independent variable, which is qualitative with only two values. The independent variable separates the sample into two groups. Each group is selected from its underlying population, and the samples drawn from the respective populations are independent. The goal is to determine whether the average values of the dependent variable differ between the two underlying populations. Finally, we can follow the example from the one sample test to estimate the 95% confidence interval of the mean difference. A confidence interval provides an estimate of the range in which the true population mean difference is likely to fall. The confidence interval equals the mean difference from the samples plus minus the critical t-value times the standard error. For our example of study strategy, with alpha equals 0.05, the 95% confidence interval is 5 plus minus 2.02 times 1.58, which gives us a range between 1.81 and 8.19. Because 0 is outside of this range, the confidence interval supports the conclusion that the mean difference is significantly different from 0.